Module 2, Lecture A, Decisions and Loops. By the end of this lecture, you will be able to write conditional statements that compare engineering results against allowable limits. Use loops to repeat calculations across loads, speeds, temperatures, or dimensions. And combine decisions and loops to classify multiple mechanical design cases. Conditional stress checks. Allowable stress comparison. In mechanical design, calculating stress is only useful when it is compared with the allowable limit for the material and design conditions. If the stress stays within that limit, the design is acceptable. If it exceeds the limit, the design must be revised. This comparison turns stress values into consistent engineering decisions. Engineers compare calculated stress with allowable stress to judge whether a part is safe, rather than relying on appearance or intuition. This applies to components such as crane lugs, pump shafts, aircraft brackets, and engine bolts, where loads may include bending, torsion, or other effects. Checking stress against material limits and safety margins gives a clear pass or fail result and helps prevent unsafe designs from being overlooked. Allowable stress comparison gives engineers a clear way to judge whether a component is acceptable. If the calculated stress is below the allowable limit, the design passes that check. If not, the design may need stronger material or a geometry change to reduce stress. However, passing one stress check does not prove the whole design is safe, because other issues such as shear stress or fatigue may still matter. The key habit is to compare engineering demands with their limits before approving a design. Python code, allowable stress comparison. This example shows how to compare stress against allowable limits to make an engineering decision. Conditional statements are used to determine whether a single bracket meets the required limit. The applied tensile load is the force pulling on the material, set here at 12,000 newtons. This load is used to calculate the resulting stress and check whether the material remains within safe limits. The resisting cross-sectional area is the material area, measured in square millimeters, that carries the tensile load. It is used to calculate the stress in the material and helps determine whether the material can safely withstand the applied load without exceeding its allowable stress. The allowable normal stress is set at 150 megapascals. This is the maximum stress the material can safely carry, and it helps ensure the design stays within safe limits. Stress is found by dividing the tensile load in newtons by the cross-sectional area in square millimeters. This gives a value in megapascals, which can be directly compared with the allowable stress limit. The remaining stress margin is found by subtracting the current calculated stress from the allowable stress. This shows how much additional stress the material can withstand before reaching its limit. The calculated stress is displayed in megapascals, rounded to 1 decimal place. This gives a clear result that can be easily compared with the allowable stress limit. The allowable stress is displayed in megapascals, rounded to 1 decimal place. This gives a clear reference value for comparing the calculated stress with the allowable limit before making the engineering decision. The code checks whether the calculated stress is less than or equal to the allowable stress. If it is, the result is marked as a pass, meaning the design is within safe limits. If not, it is marked as a fail, because the stress exceeds the limit. This simple decision helps support safety and compliance in engineering work. The code displays the outcome of a stress check for an engineering design. It reports whether the calculated stress is within the allowable limit or exceeds it, giving engineers a clear indication of whether the design meets safety requirements. The code reports the stress margin, which is the allowable stress minus the calculated stress. It displays this value in megapascals to 1 decimal place. A positive margin indicates the stress is within the limit, while a negative margin signals possible risk. The script evaluates whether a bracket can safely carry a tensile load by calculating stress from the load and the cross-sectional area. It compares the result with the allowable stress limit and reports either a pass or a failure. It also shows the stress margin, which is the remaining difference between the allowable limit and the calculated stress. Allowable stress limits. Allowable stress limits define when a mechanical design is safe enough or needs revision. They are based on the material, component, and operating environment and are kept below failure levels to account for uncertainty. In practice, these limits turn material data and design experience into clear thresholds for engineering decisions. A conditional stress check compares the calculated stress in a component with the allowable stress for its material and service conditions. If the stress stays within the limit, the design is acceptable. If it exceeds the limit, the component must be strengthened, resized, or otherwise changed. These limits vary by application and account for conditions such as repeated loading or high temperature. Allowable stress limits are based on engineering judgment, not a guarantee of absolute safety. If the limit is set too high, a design may become unsafe. If it is too low, the result may be heavier or more costly than needed. Choosing the right limit requires balancing safety, reliability, cost, and performance, with stricter limits when failure would have more serious consequences. Python code, allowable stress limits. Compare the calculated stress with the allowable limit to decide whether the design is acceptable. Use clear engineering judgment and keep any calculation simple and easy to read. We define 4 bracket stress values in megapascals: 115, 148, 151, and 190. These values will be compared with an allowable stress limit to decide whether the design is acceptable or needs redesign. The allowable stress limit is set to 150 megapascals. Each calculated stress is compared with this limit to decide whether the design is acceptable or needs to be revised. Each stress value is checked in order while tracking its case number. If a value is less than or equal to the allowable stress limit, it is marked as passing because it stays within the acceptable range. This code checks whether the stress exceeds the allowable limit. If it does, the design is marked for redesign, meaning it must be reviewed and modified to meet safety requirements. The code prints a brief result for each stress case, showing the case number, stress in megapascals, and whether the design passes or needs redesign. This gives a clear, compact summary of the stress evaluation results. The code displays the allowable stress limit, showing the maximum stress considered safe. This gives a clear reference point for comparing the stress values calculated earlier. This script checks a set of stress values against an allowable stress limit. Each value is labeled as passing if it is within the limit, or needing redesign if it exceeds the limit. It then prints the decision for each case and reports the allowable limit for reference. Allowable stress logic. Allowable stress logic checks whether a part is safe by comparing its calculated stress with the material's allowable limit. If the stress is at or below that limit, the design is acceptable. If it is higher, the design fails the check. This helps engineers make clear design and safety decisions. Allowable stress logic checks whether a design stays within engineering limits, including safety margins for uncertainty in materials, manufacturing, and loading. Conditional checks separate safe cases from those that exceed the allowable stress. A stress value equal to the limit may pass, but designers still consider whether the design is robust enough for real conditions. Allowable stress logic turns engineering calculations into clear decisions, such as whether a result is safe, marginal, or failed. It highlights cases near the limit so they can be reviewed before small changes cause problems. Used consistently, this approach helps engineers prioritize redesign, inspection, and testing, and move confidently from analysis to action. Python code, allowable stress logic. Engineering checks compare stress against allowed limits to decide whether a design is acceptable. Values exactly on the boundary typically pass, and clear status labels help communicate the result for design decisions. A list is created to store 3 computed stress values in megapascals: 85, 120, and 151. These stresses will later be checked against an allowable limit, and keeping them in a list makes it easy to process each value in turn. An allowable stress limit of 150 megapascals is used as the cutoff for evaluation. Computed stresses are compared against this threshold to decide whether they are acceptable or exceed the allowed limit. The code introduces the topic by printing a brief heading about allowable stress checks for 3 cases. This signals what the upcoming analysis will cover and helps learners follow the purpose of the next steps. We loop through the stress values while also tracking a case number for each one. The enumerate function provides both the current stress value and its sequential case number, starting at 1, so each result can be clearly identified during the loop. The code checks whether the current stress is at or below the allowable limit. If it is, the stress is considered acceptable and safe under the defined engineering criteria. The code marks the status as acceptable when the current stress is at or below the allowable limit. This indicates the stress level is safe and meets the required engineering criteria. When a stress value is above the allowable limit, the code handles it as an unsafe case. It marks the case as overstressed so it can be easily identified for review or redesign. When a stress value goes beyond the allowable limit, the code marks the status as overstressed. This signals that the condition is unsafe or unacceptable and needs attention or redesign. This output summarizes the stress check for each case by showing the case number, the rounded stress value, and whether it is acceptable or overstressed. It provides a quick way to compare each scenario with the allowable stress limit. The code prints the engineering rule used for the stress check. A stress is acceptable if it is less than or equal to 150 megapascals. This makes the decision criterion clear and reinforces the logic behind the result. The script checks stress values against an allowable limit of 150 megapascals. It evaluates 85, 120, and 151 megapascals, marking values at or below the limit as acceptable, and any higher value as overstressed. The output gives a simple engineering assessment for each case and reinforces the rule that acceptable stress is 150 megapascals or less. Loop patterns. For loops. A for loop repeats a calculation a set number of times, making it useful when working with predefined engineering values such as loads, speeds, or temperatures. It processes each item in a list in the same way and stores results consistently. By handling the repetition, the loop lets engineers focus on the calculations and interpreting the results. A for loop makes repeated analysis more reliable when the number of cases is known in advance. It applies the same steps to every case, reducing mistakes such as skipped alternatives or inconsistent procedures. This consistency supports fair comparisons in design studies and helps reveal patterns, such as how performance changes with load, temperature, or dimensions. For loops help organize engineering work by applying the same actions to many cases, such as different test points, design options, or operating conditions. This makes it efficient to repeat calculations, conversions, or checks while keeping the analysis consistent. Because each case follows the same sequence, results are easier to review, explain, and trust. Python code, for loops. For loops are used to repeat the same calculation reliably across multiple cases. In mechanical analysis, load cases are often organized as a list, and each loop pass processes one case. The code defines a list of load cases, with each case representing a mechanical load in newtons. These values describe typical forces the bracket may experience and make it easy to process each scenario later. The bracket area is set to 250 square millimeters. This constant is used to calculate material stress consistently for all load cases. The allowable stress limit is set at 4 megapascals. Each load case is checked against this threshold to decide whether the stress is within safe limits or exceeds the allowable value. An empty stress list is created to store the calculated stress values for each load case. This makes the results easy to review and analyze later in the program. A loop goes through each load value measured in newtons and processes them one at a time. This lets the same calculations be applied consistently to every load case, making the results easier to compare. Stress is found by dividing the applied load in newtons by the bracket's constant area in square millimeters. This converts the force into a stress value in megapascals, helping determine whether the material can carry the load without failing. The code saves each calculated stress value in a list, so the results from all load cases can be reviewed and analyzed later. The code prints a table header to organize the results. It labels the output with columns for load in newtons, stress in megapascals, and the final decision, making the displayed data easier to read and interpret. We use the zip function to pair each load value in newtons with its matching stress value in megapascals. This makes it straightforward to compare loads and stresses for each engineering case. The code compares the calculated stress in megapascals with the allowable stress limit. If the stress is at or below that limit, the load case is within safe margins, and the design is considered safe for that condition. This code checks whether the calculated stress under a given load stays within the allowable limit. If it does, the design case is marked as acceptable because it meets the safety criteria. When a load case produces stress above the allowable limit of 4 megapascals, the code marks it as too high. This means the stress is unacceptable under the design criteria and flags that load case for review or redesign. This code checks whether the calculated stress is higher than the allowed limit. If it is, the decision is marked to show that the load case is unsafe because the stress is too high. This line prints a neatly formatted result showing the load, the calculated stress in megapascals, and whether the stress is acceptable. The formatting aligns the values in columns and limits the stress to 2 decimal places, making the output easier to read and compare. The script checks whether different bracket load cases meet the design limit. For each load, it calculates stress by dividing the load by the fixed bracket area, then compares the result with the allowable stress. It stores the stress values and reports each case as acceptable or too high, giving a concise overview of which loads are safe. While loops. A while loop repeats a process until a condition changes, rather than running a fixed number of times. It continues while the condition is true and stops when it becomes false. This makes it useful for engineering tasks such as iterative design or simulations, where each step depends on the result of the previous one. A while loop must be designed so its condition eventually changes and the process can finish. Start with an initial value, set a clear continuation condition, and update the values each cycle to move toward completion. In design calculations, such as choosing a bearing size, the loop can test options until requirements are met, but it should also include practical limits to prevent endless repetition. While loops are useful in engineering when you need to adjust a design until it meets a target. Each cycle calculates a result, checks it against the goal, changes the input, and repeats. The purpose is to find the first acceptable solution, not just any final value. Clear limits and stopping conditions help the loop produce reliable engineering insight. Python code. While loops. While loops repeat a process until a condition changes. In this example, they are used to size a simple shaft, with safety limits included to prevent endless design searching. For the shaft sizing problem, the torque is set to 1,200 inch-pounds, and the allowable shear stress is 8,000 psi. These two values define the twisting load and the material stress limit, which are needed to judge whether a chosen shaft diameter is safe. Start the shaft design with an initial trial diameter of 1/4 inch, then increase it iteratively until an acceptable size is found. Use a diameter step of 0.05 of an inch to balance reasonable precision with computational efficiency. A 2-inch maximum diameter keeps the shaft within practical size limits and prevents the adjustment process from continuing indefinitely. An attempt counter starts at 0 to record how many diameter changes occur during the loop. To estimate the initial shear stress, multiply the torque in inch-pounds by 16, then divide by pi times the diameter in inches cubed. This gives a preliminary shear stress value in pounds per square inch that accounts for the current diameter. The loop keeps increasing the diameter while the shear stress remains above the allowable limit and the diameter has not exceeded its maximum. Each iteration records another attempt and raises the diameter by a fixed step, moving gradually toward an acceptable stress level. After changing the diameter, the code recalculates shear stress using the torque and the cube of the updated diameter. This check determines whether the new diameter lowers the stress to an acceptable level. The code compares the calculated shear stress with the allowable limit. If the stress is within the limit, it reports that an acceptable shaft diameter was found. If not, it reports that no acceptable diameter met the specified limits. This confirms whether the diameter adjustment process satisfied the design criteria. The code prints a brief summary of a shaft sizing example using a while loop. It reports whether an acceptable shaft diameter was found, how many attempts the loop made, the final diameter rounded to 3 decimal places, and the resulting shear stress rounded to 1 decimal place. Together, these outputs show the key results of the loop's shaft sizing process. The script uses a while loop to choose a safe shaft diameter for a given torque and allowable shear stress. It starts with a small diameter and increases it until the shear stress is acceptable or a maximum diameter is reached. The result reports whether a valid diameter was found, along with the number of attempts, final diameter, and shear stress, while preventing endless looping. Array iteration. Array iteration means processing each item in a collection the same way, such as applying a calculation or decision to every value. In engineering, this is useful for data like loads, speeds, temperatures, or torque values. The array holds the data, while the loop works through each element consistently to produce and interpret the needed results. Array iteration lets engineers process many design values consistently and efficiently. For example, it can be used to convert temperature readings, check safety limits, find maximum values, or count results above a threshold. The same approach applies to beam sizes, gear ratios, flow rates, and large simulation datasets, helping reduce errors and maintain accuracy. When iterating over arrays, first understand what each element represents and what result you need. You may transform individual values or summarize the whole dataset, such as finding a maximum or an average. When using multiple arrays together, make sure matching elements stay aligned, because misalignment can produce wrong results. Good array iteration combines clear logic with careful data handling to scale calculations reliably. Python code. Array iteration. Loop through engineering measurement arrays, compare each result against its allowed limits, and keep the output brief so it is easy to learn from. We define aligned lists of torque values in Newton meters and speed values in revolutions per minute. Each torque measurement matches a specific speed measurement, keeping the data organized for later calculations. The script sets the maximum allowable shaft power to 25 kilowatts, creating a limit for later comparisons. It also prepares a results collection to store each torque and speed case with its calculated power and status. This setup allows each measurement pair to be evaluated against the power limit. Before the iteration begins, the code checks that the torque and speed arrays are the same length. This makes sure each torque value matches a speed value for accurate calculations. If they do not align, the code raises an error and stops the process to prevent incorrect results. Torque and speed values are paired and used to calculate mechanical power in kilowatts. Each result is then compared with the allowable limit. If it is within the threshold, the status is OK. If it exceeds the limit, the status is high. This code adds each process design case to the results list. Each entry records the torque, speed, calculated power in kilowatts, and evaluation status, so the data can be displayed or analyzed later. The code prints a clear header for an engineering results table. It labels the upcoming columns for torque, speed, power, and measurement status, making the displayed output easier to understand. The program goes through each result containing torque, speed, power, and status, then prints them as one formatted line. Fixed column widths and 2 decimal places for power keep the output neatly aligned, making the values easier to compare. The code counts how many processed cases went over the allowed power limit. It checks each result for a high status, adds up those matches, and then prints a summary showing the number above the limit out of the total cases. This script checks matching torque and speed measurements, then calculates shaft power for each pair in kilowatts. It compares each result with a 25 kilowatt limit and labels it as acceptable or too high. The output is a concise table of torque, speed, power, and status, followed by a count of how many cases exceed the limit. Design case classification. Failure classification. Failure classification turns engineering results into clear design judgments: acceptable, marginal, or failed. In mechanical design, different loads and temperatures are evaluated against required limits, such as whether shaft stress stays within allowable levels. This helps designers quickly identify which cases are safe, which need attention, and which do not meet standards. Failure classification should reflect real engineering risk, not just simple pass or fail results. A design may meet limits but still be marginal if small changes could cause failure, or if performance depends on conditions like speed. Using consistent criteria within repeated calculations helps engineers quickly judge safety, reliability, and whether a design needs more testing or redesign. When using decisions and loops to classify design failures, clear rules are essential. A design may fail for several reasons, such as stress, deflection, or overheating, so the logic should identify the main failure mode or record multiple problems. Classifying results across operating conditions turns raw calculations into a performance map, showing where a design works or fails, and helping designers compare options, target redesigns, and communicate findings. Python code. Failure classification. Use loops to classify multiple shaft design cases efficiently. For each case, compare the calculated stresses with the allowable limits. Then report a compact engineering judgment on whether the design is acceptable. The shaft design criteria use an allowable stress of 140 megapascals as the material limit. A marginal ratio of 0.9 identifies stress levels that are close to that limit, helping classify each case as acceptable, marginal, or unsafe. The setup defines several torque cases in Newton meters to represent different shaft loading conditions, along with the shaft diameter in meters. These values provide the basic inputs needed to calculate properties such as radius and polar moment of inertia. Then evaluate the stress for each torque case. This prepares the shaft data for later performance classification under different loads. The process begins by creating counts for the 3 torque classifications: acceptable, marginal, and failed. Each count starts at 0, and a brief header announces that the torque cases will be classified by failure status before the detailed loop begins. For each torque case, the process tracks both the case number and the torque value. It then calculates the shaft's polar moment of inertia using the shaft diameter raised to the 4th power, scaled by pi and divided by 32, which indicates resistance to twisting. Finally, the shaft radius is found by halving the diameter for later stress calculations. The code finds the maximum torsional shear stress by using torque, radius, and polar moment of inertia according to the standard torsion relationship for cylindrical shafts. It then converts the result from pascals to megapascals by dividing by 1,000,000, so the stress can be compared directly with allowable limits given in megapascals. The code classifies shaft stress by comparing the calculated stress to the allowable limit. If the stress is above the limit, the design fails. If it is at least 90% of the limit, it is considered marginal. Otherwise, the stress is acceptable, helping assess shaft safety under different torque conditions. For each torque case, the program updates a running count for its classification, such as acceptable, marginal, or failed. It then prints a concise result showing the case number, torque, rounded stress value, and status, making each case easy to review. The code prints a brief classification summary, showing how many torque cases are acceptable, marginal, or failed. This gives a quick overall view of the design's performance across all tested cases. This script checks whether a shaft can safely handle several torque loads. For each case, it calculates the torsional shear stress from the shaft diameter, compares it with the allowable limit, and labels the result as acceptable, marginal, or failed. It then reports the torque, stress, and classification for each case, followed by a summary of how many cases fall into each category. Case classification. Case classification in mechanical design means sorting design scenarios by checks such as load, geometry, and material behavior. Engineers repeat calculations across cases and use decision rules to label each condition, such as whether a shaft is acceptable under given speed and torque. This turns raw analysis results into clear design guidance for selecting and improving mechanical components. Effective design classification begins by choosing the key categories that matter, then applying the same rules to every case. Whether comparing brackets, heat exchangers, or machinery operations, cases are sorted by relevant performance measures such as strength, deflection, temperature, pressure drop, power demand, and safety margin. Consistent rules make results fair, repeatable, and useful for turning computations into engineering insight. Case classification helps engineers explore large design spaces more quickly and reliably than manual checking. By using loops and decision rules, they can sort options such as bearing sizes, pressure vessel thicknesses, or manufacturing cases into meaningful categories like acceptable, unsafe, excessive, or at risk. This creates a consistent process that reduces errors and prepares results for further analysis. Python code case classification. Multiple shaft design cases can be classified by repeating calculations consistently with loops, then using decisions to turn the results into meaningful labels. We define 3 engineering limits to classify each design case: allowable stress, maximum deflection, and preferred mass. The design should stay within 150 megapascals of stress, limit deflection to 0.6 millimeters, and aim for a mass of 4.5 kilograms. These criteria provide the basis for judging each design's performance and suitability. A collection of design cases is stored so each scenario can be processed easily later. Each case records the design name along with its stress, deflection, and mass values. The 3 cases, A, B, and C, provide the data needed for later calculations and classification. A new design case, D, is added with a stress of 139, a deflection of 0.72, and a mass of 5.1. Because its stress and deflection may be near the set limits, it is treated as a borderline case for further analysis. The code first checks whether there are any cases to process. If the case list is empty, it raises a value error, so the program stops before running calculations without data. The code prints a table header for the shaft design results. It labels columns for the case name, stress, deflection, and classification, helping the output stay organized and easy to read. Each design case is checked against engineering limits by comparing its stress and deflection to the allowable values. The stress value is divided by the allowable stress, and the deflection value is divided by the maximum allowable deflection. These ratios show how close each case is to its limits and help classify its overall performance. Each design case starts as acceptable if either the stress ratio or deflection ratio is greater than 1, meaning a limit has been exceeded. The label changes to redesign required. This code checks whether a design's mass is above the preferred limit. If it is, the design is labeled safe but heavy, meaning it meets structural requirements but weighs more than desired. This flags cases that may still be acceptable but should be considered for weight optimization. This code checks whether a design case is close to its allowable limits. It compares the stress and deflection ratios to a 90% threshold, and if either one is above that level, the case is marked as marginal. This means the design is still within limits but may need attention soon. This output gives a compact result for each design case, showing the case name, stress in megapascals, deflection in millimeters, and the classification label. Separators are used to keep the results clear and easy to read. The process counts how many design cases exceed the allowable stress limit. It checks each case's stress value against the allowable stress in megapascals and increases the count whenever the limit is surpassed. The final count shows how many cases need further design attention. Each design case is checked to see whether its deflection exceeds the allowed limit. When it does, the attention count increases, giving a simple total of cases that need further review. The code reports how many design cases exceed the allowed stress or deflection limits. It prints a short limit violation count, giving a quick indication of which cases may need further attention. The script checks multiple shaft design cases against limits for stress, deflection, and mass. Each case is classified as needing redesign, safe but heavy, marginal, or acceptable, based on how close it is to those limits. It then summarizes the results and reports how many cases exceed the stress or deflection limits and need design attention. Summarizing classifications. After evaluating mechanical design cases, summarize their classifications to support engineering decisions and communication. Group each case by key conditions such as load, speed, and temperature, and identify whether it is acceptable, marginal, or overloaded. This helps reveal patterns in the design space, showing which designs are safe, which fail, and where the boundaries between categories occur. Classification summaries should give enough detail to support decisions without listing every calculation. They usually emphasize totals, proportions, main failure types, and representative examples, such as which design cases pass and which fail. By showing patterns like acceptable low-speed gear designs, high-speed contact stress problems, or pressure vessel walls that are either too weak or overly costly, these summaries turn raw results into practical engineering insight. Summarizing classifications turns automated results into useful engineering insight. It helps engineers judge whether categories are meaningful, spot unexpected behavior, and check whether results match real-world needs. These summaries support design reviews and safety assessments by showing which designs are more robust and where more testing is needed. Python code. Summarizing classifications. Summaries help turn classifications into useful engineering design insight. Loops count how often categories appear across many design cases, while decisions explain the reason each case was classified that way. Set the bracket study limits before evaluating design cases. The bracket must stay below 160 megapascals of stress, 4 millimeters of deflection, and 90 degrees Celsius. These thresholds define whether each design meets the required standards. The code creates a collection of design cases where each case stores a name along with its stress, deflection, and temperature values. Organizing the data this way makes it easy to loop through the cases later and classify each one based on its mechanical design inputs. We first set up counters to track how many cases are acceptable, marginal, or failed. We also track the main causes of failure, including stress, deflection, and temperature. So the final summary shows both the overall results and which factor most often limits the design. For each design case, we compare stress, deflection, and temperature against their allowable limits by calculating a ratio for each one. These ratios show how close each case is to the maximum permitted values and help assess whether the design stays within the defined constraints. To identify the controlling design factor, the demand ratios for stress, deflection, and temperature are compared. Each ratio shows how close that value is to its allowable limit. The largest ratio indicates the most critical factor for the design case. The controlling reason is found by identifying the largest ratio, which shows the most critical factor for the case, such as stress or deflection. That ratio is then used to classify the case as acceptable, marginal, or failed based on how close it is to the allowable limit. Each case is classified by its controlling demand ratio. A ratio of 0.85 or less is acceptable, meaning it is safely within design limits. A ratio above 0.85 up to 1 is marginal, meaning it is close to the limit but still allowed. Any ratio above 1 is a failure and requires attention. The code records each case by increasing the count for its classification, such as acceptable, marginal, or failed. It also counts the main limiting reason, such as stress, deflection, or temperature. Together, these counts support later analysis of overall design performance and highlight where improvements may be needed. To summarize the design results, first count the total number of cases being evaluated. Then, calculate the share of acceptable, marginal, and failed cases by dividing each category count by the total and converting the result to a percentage. These percentages give a clear overview of how the cases are distributed across the 3 outcome categories. To find the most common design limit, the process compares how often stress, deflection, and temperature each controlled the design. It uses the maximum count in the reasons record to identify the constraint that appears most often. The result, called the dominant reason, shows which design factor most frequently limits performance. The classification summary reports how many design cases were evaluated and how they were categorized. It gives the count and percentage of cases that are acceptable, marginal, or failed. It also identifies the dominant controlling limit, which is the most common factor restricting the design. The logic turns design case classifications into a practical engineering recommendation. If failed cases outnumber acceptable ones, it advises reviewing the design before production. If failures do not dominate but some cases are marginal, it recommends investigating those near the allowable limits. If all cases are acceptable, it reports that the design has a comfortable margin. The code outputs a short interpretation of the design case results. It compares failed and acceptable cases, checks for any marginal cases, and then recommends whether to review the design, investigate borderline results, or proceed with confidence. This script checks bracket design cases against limits for stress, deflection, and temperature. It classifies each case as acceptable, marginal, or failed based on the worst ratio of actual value to allowable limit, then summarizes the counts and percentages in each category. It also identifies the most common limiting factor and gives a recommendation, such as reviewing the design, investigating marginal cases, or proceeding with confidence. In this lecture, you learn to write conditional statements that compare engineering results against allowable limits, use loops to repeat calculations across loads, speeds, temperatures, or dimensions, and combine decisions and loops to classify multiple mechanical design cases. In the next lecture, Lecture B, we will go over writing functions.
Thank you for your attention. See you all in the next lecture.